Hello, welcome to another problem session. So today we have a problem from this website. You can go check that website out if you for more problems. So let's read the problem. Of course, your eyes goes in the figure, it comes with the problem. So we have a wheel. This is the wheel, and it's supported with something in the center, and there is several turns of a light thin non-sticky tape. Non-sticky tape so it is a non-sticky tape. I think it's like this, several turns over here, and then you attach a block here, but the mass of the tape is 0. Tape is 0. If it's not 0, then it becomes a different problem. Okay. Another thing is when the block is released, first you're holding them, when holding this thing, so you're holding by your hand, you're holding here, t less than 0, you're holding it, and then at t equal to 0, you let go. It's important always to think in terms of time. So it's like there's a time before which it's going nowhere, just everything is static, and then suddenly you let go. And so there's a time in which this whole thing is coming down while this may be rotating. Unwinds smoothly and wheel rotates. So there may be a friction over here at the axle, but that's you're supposed to say frictionless here. That's an assumption, so we can make use of that, so we can ignore any forces of friction here. So what are we trying to find here? We're trying to find angular acceleration of the wheel and the tension in the tape. So we're trying to find at some time t greater than 0, we're trying to find the acceleration alpha as this wheel is rotating. So all right, how would we proceed? Because we have to find a tension and angular acceleration, we're probably in the territory of using laws of motion rather than energy. So let me see if we can do this motion of this and motion of this. So they're like two different objects. Sometimes you can have the motion together and then you can solve it. That makes sense. But here, because we're going to do equations of motion, it probably is better to do equation of motion for this, because this will be a rotation, pure rotation, and so this will be pure rotation, and this guy will be translation. So one of the things we can notice immediately is if this rotates by an angle theta, then this would move a distance. So this is delta theta. Then delta, say this is y-axis. So just say the distance moved will be, the distance moved will be, this distance will be, if the radius is r, then this, whatever the distance on the arc is the distance this will have moved, and that will be r delta theta. So they will be kind of related. Delta theta there will result the distance traveled here. So if I say this is kind of say positive angle and this is a positive distance, then we might say, okay, how about we just pick an axis that points down like that. It's the y-axis. Y-axis, this origin, and the y-axis points down like that. So this may be just a used to be y equal to 0 at t equal to 0, but at some time t, there's the distance traveled, right? Okay, I hope that makes sense. So upshot is a rotation of pulley and about the axis, we're talking about this axis. Rotation pulley about an axis through center of mass. That's the center of mass of the pulley, through center of mass and perpendicular to pulley. So that's the rotation. Delta theta is related to y covered by block in the same amount of time. So delta y. So delta y is r delta theta. So if this is positive, then this is positive. The way we just make sure that the two coordinate system are kind of related. One coordinate will be for rotation. So one coordinate system for rotation and one for translation. Okay, so this is important in time delta t. Okay, this will tell us that Vy of block is r omega of pulley just by dividing by delta t. So you take this, divide by delta t, that will give you that. Now if I take a derivative of that, then I'm going to get ay is equal to r alpha if I do ddt of this. So this will be a angular acceleration. So signs are important here. So we say this is the positive direction. So we're looking at a clockwise as positive here. So we're going to just call clockwise positive. And the y, we're going to point it downward. That's positive. Y positive downward for this guy. And clockwise positive is for alpha. So what we found is alpha positive for clockwise and y positive downward. So that's the notation for us. Now we can use this equation with the equation of motion for the two blocks. So let's see what happens with block. We have y-axis is pointed down like that. That's our notation. mg is down like this for the block, little m. And then we have a tension like that. And the acceleration is that way. So we're just calling that ay. So mg minus t is AY, MAY. So this is equation 2. For pulley, we have a rotation, so and this is a rigid body, and axis is through the center of mass, so we already know moment of inertia for this, and this will be simply I alpha is I about the axis, alpha is going to be the torque net about that axis. So if you look at forces on the pulley, so here's the pulley, so there is a tension force this way, there's a gravity weight for the pulley like that, and then if these were the only two forces, you would be probably looking at pulley just going down, but there is a normal force from the axle at the center, and since the axis goes through the center, these guys have zero, this guy torque is 0, so only torque is from this, and to find that torque we have to, as you know, extend this line, and from here we draw the lever arm. So the lever arm is just the radius here, and because this is counterclockwise, I mean clockwise sense, so if so this is clockwise sense for the torque from tension, and clockwise the way we have determined is going to be positive, so that's going to be T times R as a positive, and I, what is the I going to be? It's going to be a disk through the center, so it's going to be half mr square and then alpha. So we can either change this to that or alpha to that, maybe AY to that will go over here, so and change AY, and that's going to be M R alpha. So from these two, we should be we should eliminate T and get an alpha, and so let's do that. This one of the R got cancelled out, and so T put in there, becomes mg minus half mr alpha equals to mr alpha, and then can solve for alpha is little mg divided by m plus half big M R. So that's the alpha. The tension in terms of alpha, so that's we can solve that. Putting this back in here, we will get tension is equal to half mr times this whole thing, mg over little m plus half m times r, and of course this r cancelled out. So that's the other answer we get. So we're done with the angular acceleration. That's the answer for angular acceleration. Then we're done with the tension. And if we were asked to get the acceleration for this block, we'll just use this to get the acceleration. Okay, so this is a very standard problem. Let's go over one more time as to what really was important parts of this problem. So this part here, all the way leading to this is called constraint in the system. And because there is the way it's unwinding, the way the tape is unwinding, and the tape is coming down and the pulley is rotating, the amount of distance around the circumference is how the tape is, amount of distance the tape would move. This is a very critical observation, and from there we can say the angle that the pulley will be rotating is actually related to the distance traveled. If the tape was unwinding at someplace else, it will be that distance, but it's unwinding at the edge, right? So it's actually at this place that the distance at the arc there must be equal to that. That's actually very critical. Once you got that critical thing done, and that was done in some time, and divide by time, you can get the speeds have to be the same, related, and so the accelerations have to be related. And this is what goes into equations of motion. So we got one equation of motion like that, another equation of motion like that. And getting the equation of motion was really not that hard, but the sign is important here. So make sure that the sign is important. For the sign, you can pick a notation that actually is consistent with each other. For instance, I couldn't pick, if I did this as positive, I couldn't pick y going up as positive. They would be inconsistent with each other. So if I pick this as counterclockwise, so another will be, say, counterclockwise positive, then all of this will be negative here for us. Then then I would say y positive will be upward. So we could have chosen that, but the way the problem is set up here, I think this is more is simpler because I don't have to write extra minus signs to cancel. Okay, with that, I'm going to stop here and we will see you in another video. Bye.